So, welcome back to my YouTube channel. We want to prove in this video that the expectation of the maximum of normal random variables divided by the square root of 2 times the logarithm of n converges to 1. In the previous video, we showed that the expectation is less equal than the square root of 2 times the logarithm of n. So what we need to show now is that essentially this is the definition of a limit, but we know that we don't have to take the absolute value because we already know that that the expectation is less equal than the square root, which makes this expression less equal than 1. So what we essentially have to show is, because we have that the absolute value is just 1 minus this fraction, that there exists for all epsilon a capital N such that for all n that are greater equal this capital N, that this expression holds. So this is the same as, for example, if we divide the square root term on both sides, that leaves us with 1 minus epsilon is less equal than the ratio. And then if we bring this ratio on the other side and then the epsilon, we just have this expression right here. What we can do is that we replace the epsilon by epsilon tilde, which is defined like this. This is a monotone. Transformation. So whenever we pick epsilon, we have an epsilon tilde, but for all arbitrary epsilon tilde, there's also an epsilon. So when we show convergence for all epsilons, that's the same as showing the convergence for epsilon tilde. But actually, we don't need this step to be precise. Like instead of proving this, we can also prove this. This is just what I just mentioned by the transformation. But now we want to have a look at this expectation, how we can somehow lower bound this with an expression that somehow depends on the square root term. So we define in event capital A indexed by n and epsilon that are all omegas in capital omegas, such that the random variable inside the expectation, so the maximum overall standard normals, is greater equal than the square root of this term, which we can also write a bit more compactly this way. So when we now want to compute the expectation or approximate the expectation of the maximum, we can use conditioning on this event. So we condition on capital A and epsilon, and we have to take the probability of capital A and epsilon, and this we do this also with the complement. So the complement will just be the event where the maximum is just less than the square root term. And now we have a closer look at every term in this expression. So the first term we can just low bound this by the square root of 1 minus epsilon times 2 times the logarithm of n, because we're conditioning on the event that the maximum is greater equal the square root, so we can low bound this by just plugging in the square root term. So this is quite easy. And the other one is this term, so we can lower bound the maximum of random variables by just picking one. We just pick the first one. I mean, it doesn't matter because they have all the same distribution and they're independent. So this we can just low bound by the expectation, the conditional expectation of one standard normal, given that the maximum of all is less than the square root term. And this is the same as just having the relevant standard normal being less than the square root term, just because of independence. So it doesn't matter what G2, G3, G4, and Gn do, if they are larger than the square root term or not. Just depends on what G1 does, and this conditional expectation we can compute. So in general, when Z is standard normal, this conditional expectation is just the probability of Z less than A times the conditioned expectation. So this is just the expectation of Z times the indicator function that's 1 when Z is less than A. We can rewrite Z times phi of Z. Phi is the PDF of standard normal function, so it's 1 over the square root of 2 times pi times the exponential of minus z squared over 2. It's quite easy to see that the derivative of the PDF is linked to the original function, so we can rewrite this in terms of the derivative with a minus sign. So we have an integral, the derivative, they cancel out, and we have this expression. And what's important is that A, it's negative, because this is always positive, this is always positive, so this is a negative negative value, which makes sense, because without a conditioning, the expectation of the standard normal is 0, but when we have the extra information that Z is less than a certain value, then it's reasonable that the expectation will be less than the expectation without any information, so slightly less than 0. But in the limit, so when A goes to infinity, that one goes to 0, because this goes to 1 and this goes to 0. So actually we're just done with this part, because we know that this goes to 0. The probability of something is between 0 and 1. So the product is also converging to 0. So this is also already a good result. So now we have to make sure of this probability, and for that we're just looking at the complement. So the complement is the probability of the complement is the probability that the maximum is less than the square root term, which is nothing else than all GIs are less than the square root term, but because of independence, this turns into a product. This is why we have the probability of G1 less than the square root term to the power of n. Okay, great. Now we can write the probability as 1 minus the probability of the complement. And now we use the fact that 1 minus y is less than or equal than the exponential of minus y. It's better known for 1 plus x less equal than e to the x. So this is the same, just with a minus sign. But here we have this 1 minus y. So we can upper bound this by the exponential of minus y. And then we have the to the power of n term, which just turns into the product here because of the exponential function. And what we're doing now is using the Mills ratio. So the Mills ratio bounds for a standard normal the ratio of the probability of z greater equal than z over phi of z. So phi is again the PDF of the standard normal, and this can be bounded in two ways, by 1 over z and by z over z squared plus 1, which can be easily verified by just taking derivatives and seeing that this has to be true. So this is an easy problem to try yourself. So we use that here on this is our p of z greater equal this z. So we use the Mills ratio with z over z squared plus 1, which turns into this expression. So z over z squared plus 1, and here the PDF of the standard normal, and the n just stays there. And what we now have to what we now want to show is that this whole expression converges to infinity, because when we show that this converges to infinity, so all to negative infinity, means that all of this converges to 0. Hence, this is converging to 0, and the complement to 1. For that, we plug in this square root term into the PDF. Everything in the exponent cancels, and we're left with the constant PDF term, the 1 over square root of 2 times pi. And then we have this n, which is here, and the n to the power of epsilon minus 1 is just the remainder of plugging in the square root term into the PDF. So this is also very easy to see. And now we want to compute this limit. We do this by using the rule of L'Hopital. So in the first step, we just derive the the top and the bottom. So the top is fairly easy, just with respect to n, and the bottom, when we derive the square root term, we're left with this. And if we just rearrange this term right here, it looks like this. So we get these 1 over n's on both terms. We just pull them up, so we're again left with n to the epsilon. But on the bottom we have expressions like this expression and this expression, which both converge to 0. So after all, this is a diverging series converging to infinity. So in the end, this is also converging to infinity, meaning that this whole expression converges to 0. And after all, the probability of capital A and epsilon converges to 1. So what we have shown now is that this is converging to 1. This whole guy is converging to 0. And now we want to make now we want to use all of this to essentially show this converging criteria. So what we've shown so far is that we can lower bound the expectation by the square root term times something that is converging to 1, which was the probability of capital A and epsilon, plus a sequence that is converging to 0, which was the second term of the conditioning. If we divide on both sides by the square root term, we're left with the 1 minus epsilon, and then the alpha term, and then the beta term, but divided by the square root of 2 times ln n. But this is again another sequence which is also converging to 0, so we can just rename them and just call them beta tilde and alpha tilde and epsilon tilde. And the whole expression we call gamma tilde. And of course, this is converging to 1 minus epsilon tilde. So because this is converging to 1 and this is converging to 0, so after all, this is converging to 1 minus epsilon tilde for all n. So we're already pretty close to our target, because we wanted to show that this holds, or if we put this on the other side, that the fraction is greater equal than 1 minus epsilon. But now we have that the fraction is greater equal than a sequence that is converging to 1 minus epsilon tilde, or epsilon. But we'll show now that this is no problem, and implies the criteria we want to show convergence with. So we just let epsilon be greater 0. And we know that this sequence is converging to 1 minus epsilon tilde. So the gamma tilde indexed by n and epsilon over 2 is converging to 1 minus epsilon over 2. This means there exists a capital N such that for all n that are greater than n, that the absolute value of the difference to the limit is less than uh, a certain value, which we choose to be epsilon over 2. Absolute value means this holds in both directions. So for gamma minus this term and for this term minus gamma. So this implies that one minus epsilon over 2 minus gamma is less than epsilon over 2. Rearrange that and we get gamma is greater than 1 minus alpha, 1 minus epsilon, because we combine this epsilon half and this epsilon half, which gives us 1 epsilon. So in the end, we actually have that the fraction is greater equal than 1 minus epsilon. So in the end, we showed that for an arbitrary epsilon, we find a capital N such that for all n that are greater than this n, that this expression holds, which is the same as saying that the limit of the fraction is equal to 0.